Sattler, who is original German, but now working at the Czech Technical University in Prague. And his field of expertise, I heard for many years, is visual localization. So I am really glad that we have one of the best experts in Europe regarding this topic. And I can't wait to see all the stuff you will show us. So the floor is yours, Thorsten. And Thorsten will be leaving soon after his talk. So if you have questions regarding this topic to Thorsten, make sure that you catch him really quickly because he won't be there for dinner anymore. Okay.
Thanks for the nice introduction. Yeah, I'm Thorsten. I'm going to talk about, well, you clap afterwards if you still feel like it, right? So don't give me undeserved applause or something that I haven't delivered. So I'm going to talk about visual localization, partially about privacy preserving visual localization. If you have any questions, feel free to stop me at any point in time. We'll discuss it then, and if it's something longer, we take it offline. Let's start with like a short definition of the visual localization problem. So the idea is you're given some image and some scene representation, and what you would like to do is you would like to estimate the exact position and orientation from which this image was taken with respect to the scene. Why would we want to do this? It's very useful for augmented reality applications. This is something that we published a couple of years ago, where the idea is we localize the current view of the user with respect to a 3D model that we built, and this allows us to place those virtual objects inside the field of view of the user in a way that it looks like this would be part of the real world. So this was our small academic demo roughly 10 years ago. You can see similar things also based on visual localization. Nowadays, if you have a Google phone, there's on Google Maps there is I think it's called Live View or something. If you do navigation, walking through a part, you can get the phone up, take a picture. It will try to figure out where you are in the world and then give you instructions on where to go. Similarly, the same techniques are useful for robotics, self-driving cars, other autonomous drones, other robots. What I think is also an interesting application is actually doing some sort of performance capture of humans. So this is a paper that we recently put on arXiv. The idea is we have a user equipped with a head-mounted camera, which is doing localization, and multiple body-mounted IMUs. And we use the IMUs to essentially model interactions between the user and the scene, such as sitting down on the scene, opening doors, opening cupboards, and so on and so on. What's interesting here is that we're really only using the camera to place a human in the scene. The rest of the interaction is really only based on IMU data without actually any visual feedback. The motivation is that a lot of interaction actually happens without you looking at. So if you open doors, you're not always looking at the door handle. You're not doing, let's close it, but you would just open it, walk through it, and then forget what you're doing with your hand. Okay, so I hope that convinced you that localization is an interesting problem. Let's look at solutions to the localization problem. Since we live in the age of deep learning, one obvious approach is, well, I'm going to train a network that takes images as input and throws out a camera pose. We typically call this camera pose regression. We can easily generate training data using structure for motion algorithms, which take many images as input and then estimate the camera position orientation from which those images were taken. And then these positions and orientations together with the images form the training data. You're essentially training the network to predict precisely these positions and orientations. And you can essentially all camera pose regression techniques that were available up until I think last year, you can break down into few, into the same schematic. Here the image goes into a fully convolutional network that is doing some sort of feature extraction. You embed the response from the last layer into some high dimensional space. And from that high dimensional space, you do a projection into camera pose space, meaning you get a position orientation, typically like a 6 or 7 dimensional vector. And let's look a bit more in this embedding and projection part. So this projection is nothing else than you start with some like vector in a high dimension space. This is your embedding. You multiply it with a projection matrix to get to a lower dimensional space, and you add some bias term that allows you to shift things, and that is your predicted camera pose. And the predicted camera pose is essentially part of this is camera position, part of this camera orientation, meaning you can actually interpret the first couple of rows of the projection matrix as information pertaining to camera positions, and the last rows to information pertaining to rotation. If you write this out, what the network actually learns is it learns to do the embedding, and it learns this projection matrix. And once it has this projection matrix, what you get as a predicted pose is essentially a linear combination of the individual columns of the projection matrix. So essentially you can understand each column of the projection matrix as some base pose, and the network learns the set of base poses and how to interpolate between them. So it's really doing something very simple. It's not necessarily geometric reasoning that it learns, but it's learning interpolation. Yep.
Do you have to somehow restrict or regularize the learned projection matrix in order to get this nice position and rotation?
So you typically have some loss term that says my rotation should be like a unit quaternion or something like this.
So you introduce something like a loss function to have like position and rotation nicely separated?
No, I mean this emerges automatically because you get the vector out and you say the first couple of entries is my position, the last couple of entries is my rotation. So it's by design, not thing that emerges. So let's look at a simple example. We recorded this in Prague. There's on the right the training trajectory was recorded on street level. Test trajectory is walking up from river level up to sea level, up to street level, up a ramp. Can anyone guess whether the network will be able to predict accurate the test poses accurately, or will something bad happen here? Any guesses?
Well, because the base position for like a basis,
Yeah.
You cannot actually reconstruct the testing position from the basis we have, so that it's impossible.
Exactly. So what the network learns, as I said before, is it learns the set of base poses that explains the training images. And in this case, the training images are roughly on a line, so it learns that all the images that it will ever see will be roughly on a line. So the base pose will be oriented on a line and can never really escape here. Here's a visualization of this. You see the training trajectory in a top-down view, the test trajectory. You see the ground truth test pose as the green dot, the predicted test pose as a purple dot, and the pose of the most similar training image as a red dot. And then you see the actually video playing. And what really happens is that rather than predicting something that's on the test trajectory, it predicts something that's stuck onto the training trajectory. And since you can also visualize this base position part in the projection matrix, so that's shown here. The color coding is warm colors mean this base pose has a large impact on the predicted pose. Cold colors means less impact. Large dots means a lot of impact. Small dots mean small impact. And what you can see is that essentially it learns to like all the base positions are oriented along a line, and it never really escapes this line. Linear combination of points on a line are still a point on the line. Okay, you can argue that we actually tricked the network here. We didn't record much data. So that's mean of us. We tried to look at a more complex example. This is St. Vitus Cathedral in Prague. We essentially walked around this for training, and then for testing we walked a bit in the courtyard. If you look at the training, like the position part in the projection matrix, you see that this nicely resembles the structure of the trajectory that we walked. All these base poses shown here for two networks are roughly in a circle or in an ellipsis. So in theory, you should be able to predict any point in this plane because you have a basis that forms that spans this. However, if you look at the actual predictions that the two networks make, then you can see that they're actually rather close to the original training poses. It's not really generalizing to test poses. And the thing here is that, yes, all your base translations or base positions span the whole space, but you're not allowed to use them to some degree. So through this embedding part, you learn a coupling about how the appearance for images of a certain appearance, you're only using a subset of the base positions. So you're still stuck into something that's locally not enough to explain all motions. So this simple approach of just we train a network and that will solve our problem, which works in a lot of areas of computer vision, is not working that well in this area of visual localization. And you can actually also try to quantify this a bit. So we can compare it against two baselines. The first one is simple. Rather than trying to do any complicated prediction of a test pose, we do image retrieval for a test image. We find the visually most similar training image and then just say that pose is a reasonably good approximation to my test pose. So here I would, for example, retrieve this training image. Or I could actually also try to retrieve multiple training images and then interpolate their poses and then say this interpolated pose is hopefully a better approximation. Second baseline is what we call structure-based localization. I'll go into the detail about this later on. The idea is that you have a 3D model of the scene for a given test image. You establish correspondences between pixels in the test image and 3D points in the scene, and then that allows you to do precise camera pose estimation. So let's compare this pose, what was back then the state-of-the-art pose regressor, with both baselines on synthetic data. So what we did here is the large red pyramids correspond to the poses of real training images. We use these training images to build a 3D model, and then we render training images and test images from the original poses. So here the green pyramids are poses of the test images, and in order to see how the availability of data impacts performance, we also rendered additional training views shown here as the small red pyramids. And these are results expressed as median position and orientation error for the pose regressor, which is the first row, like a simple image retrieval baseline and the structure-based baseline. And as you can see that both retrieval and pose regression benefit from more data, but they're still significantly worse than the structure-based method. And also this pose regressor is not really much better than a retrieval method, which is something that you can also see on real data. So what you see here is our median position orientation errors averaged over 7 scenes. The green dots in the bottom are structure-based methods. All the other dots correspond to various pose regressors, and the vertical and horizontal line correspond to median position and orientation error for retrieval baselines. And you see that these methods are much closer to retrieval. So it's like a very simple pose approximator compared to like a method that really does precise pose estimation. And particularly the first regressors are actually really bad. They're not even better than just taking the pose of the most similar training image. So hopefully that convinces you that, different from many other areas in computer vision, this is nothing that, localization is not an area where you just say, I train a network, problem solved. Rather, we have to be a bit more clever what we're doing. So let's look at structure-based methods, which is what currently constitutes the state of the art. So the idea is that we start with a 3D model that we've reconstructed from images using structure for motion, meaning each 3D point is actually reconstructed from features extracted from 2 or more images. So each point is essentially a position, and we can associate it with local features that we extracted from the images. If we have a test image, we can use these local features associated with 3D points to do 2D, 3D matching. So we first detect features, we try to figure out what's interesting points in the images. In the image, we compute descriptors. We use these descriptors to find correspondences between features in the image and 3D points in the model by essentially comparing the descriptors associated to both of them. Once we have them, we can do camera pose estimation by essentially running a pose prediction algorithm inside a robust estimation loop. And then that gives you essentially the position orientation from which the image was taken, together with the 2D, 3D matches that are explainable by this pose. I also like to call this pipeline the old school localization pipeline, because many of these components are actually rather old. So like feature description and detection, you get very good results still up to this day with the standard SIFT algorithm, which was first published in 1999. Like descriptor matching can be done efficiently using KD trees, which is from the 70s. And actually the first solutions to camera pose estimation from 2D, 3D correspondences go back to the 1700s. So this is really nothing new. This is just combining existing things. And it still works up to this day. If you want to scale this a bit, you typically combine structure-based methods with image retrieval. So rather than comparing descriptors extracted from this query image against all 3 points, where you might have millions of them, you exploit the fact that this 3D model was actually reconstructed from images at some point. So you first try to do an image retrieval step, where for the given query image, you try to figure out what's the visually most similar database image. Then you can do feature matching between the query and the retrieved database image. And since you know which of these features in the database image were used to build the 3D model, which correspond to 3D points, you actually get the 2D, 3D correspondences that you need for camera pose estimation. So again, nothing fancy, but it's still something that scales well and that works to this day. Nowadays, you would use local learning for individual components. So this is a state-of-the-art localization pipeline where they use a neural network to extract both global and local descriptors for the database images, and the same network is then applied on the query side. It extracts a global descriptor, which you can use for image retrieval, and then the local features that you also get from the CNN are used to do the 2D, 3D matching to get the correspondences that you need for pose estimation. So these are 2 ways to solve the localization problem. There was this camera pose regressor and the structure-based methods. There's much more, and you can roughly classify localization methods based on how they represent scenes. So one side is image-based representations, which contains this retrieval, contains image retrieval, contains pose regression, where your database is you represent the scene essentially as a set of images with known poses. Or you can have structure-based methods where you actually are more interested in representing the 3D structure of the scene, and forget about the images. Or you can have something hybrid, for example, these image retrieval-based structure-based methods that represent the scene both the scene geometry and like the images that we use to build this. So all these methods that I've presented that are on this slide essentially assume that you have built your 3D model from images, and then you can associate new images with information stored in this model. What we recently discovered is actually that you don't necessarily need to build your 3D model from images, but local features are actually quite good, that you can match features between real images and renderings of 3D models. So on the left is you have a textured model. On the right, you have raw geometry. And you can still, in many cases, find enough correspondences to do accurate pose estimation, which I think opens up interesting questions, especially given that you can download like a lot of 3D models of different places in the world from the internet by now. And we started looking into if you start downloading things from Google Warehouse or from Sketchfab, what's the type of 3D models that currently allow precise localization? So do we need accurate texture? Do we need accurate geometry? What's the level of detail that we need? If you're interested in this, we will present this work at CEPR this year. The paper is on archive, and we're going to make our benchmark publicly available. Okay, so I hope that convinced you that localization is an interesting problem. What I've talked so far is a bit about how localization methods work, how they are structured, how they represent the scenes. What I think is a very interesting topic that's a bit orthogonal to this is that of user privacy in the context of visual localization. Because nowadays, what you would typically do is a typical localization system that Google provides, that Niantic provides, that Microsoft provides works by you capture data on some edge device, could be a phone, could be a HoloLens, some AR goggles, VR goggles. You send data extracted from that image to a server, and the server then returns a camera pose. And that poses a couple of potential privacy risks. So the most obvious thing is if you send an image to a server, whoever has access to the server can see what you're seeing all the time. So he or she might see things that you don't want them to see. So a malicious server might learn from like private related things that you don't want to share. One obvious answer could be that, well, I don't send an image because the server will later on extract some local features anyways from it. I could do the local feature extraction and send the image, the features to the server. That unfortunately does not preserve privacy. There's a very interesting paper that shows that if I have a set of local features that I can project into images, and this could just be features that I extract from an image, or also features like associated with 3D points in a structural motion model that I project into an image, then I can just take these sparse projections that you see on the left and still from them recover the original image quite accurately. It's very close to the original image from this very sparse input. So whether you send an original image or just a set of features that extract from it, from a privacy standpoint, probably doesn't make a difference. Because if you have enough, if you have these features and you have enough of them, you can actually recover the original image. So there is some interesting work to be done here. So as I said, sending an original image or sending features is both not a way to preserve privacy of users. There is some interesting work, not too much, on finding some privacy-preserving representations for images that prevent this recovery of image content from local features. I will talk about this in a few slides. I'm not 100% convinced that they're actually privacy-preserving. I think we have a way of recovering data from this, but this is currently, that's just a hunch. I can't prove it at the moment. Another potential privacy risk is actually the data that's stored on the server. So if we're talking about data that's captured in cities, and this probably doesn't pose a privacy risk, but the idea of this cloud-based server is that it will actually eventually also store user-generated data. So someone might use a HoloLens to capture their house, and then they might want to use that data to play some AR game, or they might want to share it with some friend who's visiting, or some some service robot that needs to localize in the scene. So, and then storing, we just saw this, storing a sparse structure motion point cloud on the server also poses a privacy risk because you can recover images from this sparse point cloud. And there was some very interesting paper in 2019 that proposed a potential solution to this. So let's look a little bit into this. And the idea is pretty simple. Rather than storing like a 3D point cloud where each point is associated with local features, we store a 3D line cloud where each line is associated with local features. And the idea is that from the standpoint of estimating a camera pose, it doesn't really matter. I can still estimate a camera pose from correspondences between pixels in an image and lines in 3D. But if you look at these lines, you end up with a representation that's, at least for human, non-intelligent. So if I would just show you these lines, you wouldn't be able to say what's actually in the scene. So their method works like this. They start with the original point, and they in a point cloud, and lift it to a line by essentially choosing a line direction uniformly at random, and then defining a line that goes in that direction and passes through the point. And if you look at a single point or a single line, this is perfectly privacy preserving because you don't know where along the line your original 3D point is. But we're not giving a single line, we actually have many lines. And it turns out that once you start having multiple lines, you can recover the original points, at least approximately. And the method that we propose for this is based on a very simple observation. If you take 2 points and randomly have lines passing through them, or with random line directions, then quite often if you find the closest distance between those 2 lines, and then the closest points between those 2 lines, then what we observe is that quite often these closest points along the lines are a good approximation for the original points. How good the approximation is depends on the distance between the lines. The closer the line, the closer the distance to the line, the better. What was that?
I have no idea.
So if you have multiple lines, what you can do is some sort of figure out where your point is by looking at density of closest points. So for each line, like if you want to recover a given point, you look at all other lines or a subset of these lines, compute closest points, figure out where they lie on the line, and then essentially find clusters of where closest points are close by to each other, and from that compute an approximation of the original point. Here are some results. On the left you see the original, on the top you see the original point cloud and images recovered from this original point cloud. And then on the bottom you see the point clouds that we recovered from a line cloud, where you lifted the original point cloud, and then images that were rendered from this recovered point cloud. And yes, we lose detail, but overall you can still see that there's a lot of the original content is preserved. And that also applies to indoor scenes where you typically have much sparser points because a lot of structure indoors is weakly textured or barely textured. Still, we get a reasonably good approximation of the original point cloud from just by recovering points from lines to a degree where you can still see that there's some shoes on the ground and so on and so on.
I have a question.
Yeah, sure.
Does this modified privacy-preserving algorithm provide some complexity increase in the position retrieval, or is it complexity-wise pretty much the same as to using the point cloud? In terms of establishing correspondences between pixels in an image and lines in the model, there's no difference because you just do descriptor matching, and for that it doesn't matter what is attached to it geometrically wise. If you do pose estimation, I think so. If you have point-to-point correspondences, you need 3 correspondences for pose estimation. If you have point-to-line, you need 6. And that makes it a bit harder if you have changing conditions. So one image is taken by night and you reconstructed your model at day, because you get fewer correspondences and you get more wrong correspondences. But accuracy-wise, you can still get very, very accurate reconstruction, like pose estimates.
Okay, thank you.
Yeah. Any other questions so far? No? One thing we noticed is our recovered point clouds get worse if we operate on sparse line clouds. I mentioned this before. If our approximation of the position of the original point based on closest points between lines is better if the original points are closer to each other. If you sparsify this original point cloud and then lift it to line cloud, you increase the distances between the original points and your approximations become worse. That's especially if you use like between 5 and 1% of the original points, which is interesting because localization is still possible if you just have a very sparse point cloud. But it seems that things start to become like much more private once you use a subset of all available data, which is intuitive because you're throwing a lot of information away. So what you see here is like the images that we recover from sparse line clouds. What's interesting to point out is that the images recovered from sparse point clouds are also not much better. So it seems that sparsity is much more important if you want to preserve privacy than how you actually represent the scene. So the original way of representing the scene as a point cloud might as well be quite privacy preserving if you just have very few points that are sparsely distributed in the scene. In general, I would say this is still very much an open problem on how you represent a scene in a very while ensuring that you can estimate camera poses accurately, while also ensuring that a potential attacker could learn nothing from the scene. So here, the original way of preserving privacy was to lift points to lines into 3D. You can do the same thing in 2D. By saying if I extract local features rather than storing the position of the local feature in the image, I lift this 2D feature to 2D line and then store line positions. That still allows you localization and leads to representations something like this on the right. And in this case, this attack that I just explained doesn't work because it's essentially depending on the fact that if you have randomly chosen lines for 2 points, they rarely intersect in space. And typically, they just pass each other close to the original points. In 2D, this doesn't work. In 2D, lines are either parallel or they intersect. We still have some ideas because so far we have only used geometry. We haven't used the local features associated to those lines. I think once you take them into account, you can try to figure out which lines correspond to points that should be close by, and then you should be able to at least get a good approximation of the original image. But let's see. We'll know more in a few months. So looking at this image of privacy, what we've talked about is the data that you send to a server can expose information from you. The data that's stored on the server could expose information. But it actually turns out that also this camera pose that's returned by the server can tell an attacker about what's stored on in the cloud. So this is a potential source of a privacy leak, where if you upload a map to a server, some attacker might actually be able to learn what's stored in the scene without actually having direct access, and using just this information that a localization service is actually supposed to provide you. And this potential privacy leak is actually a downside of the fact that we would like our localization algorithms to be robust. So what you see here is feature matches between images taken under very different conditions, so day and night, like a very blurred version of an image with an unblurred version. So we would like to have feature matching that is robust under these conditions. So we would like feature matching that's robust against appearance changes and slight changes in geometry to handle like blur. What this also typically implies is that you start matching things that are not identical but similar. So different versions, like different copies, if you want to speak of this, of a chair, or slightly different chairs that are still very similar. And this can be exploited to actually figure out what's stored in the scene without having access to the scene, but by just querying the localization server with images. So the idea is this: the attacker, if you want to call it like this, has a sequence of images of the same object. It then builds a 3D model from these images and uses the images to query the server. The server will return camera poses, which are probably not that well visible here. It's the pink dots. And given those poses that you get from the server and the pose that you get from structure for motion, you can try to place the object in the scene and try to figure out where is the object. And that works. You don't necessarily need exactly the same object, but something that's reasonably similar. And that allows you to try to place objects in the scene. So here you see the query image, or like an example of the query image, the example of the type of object that's actually in the scene, and then the placement, both the ground truth and the placement that we get with different local features. You can see that it's not like super precise, but you get a very good idea of what's in there and how is it placed. And you could later on start reasoning about the placement of objects based on saying, for example, a PC, like a monitor should always be on a desk or something. So you could refine it potentially. Here is another example where you see the actual objects in the scene, and here you see the roughly reconstructed scene based on the objects that are present. Here's another example from two scenes. On the top you see we were able to roughly place, I think it's the oven. It's not precisely there, but you roughly get an idea of where the oven is. And in the bottom we were able to place a couch, even though it's a rather different model than what's actually in the scene. So if you want to ensure that like user-generated content that's uploaded to the cloud remains like that, no one can access data from it. It's not sufficient to say I'm ensuring that no one can access my data on the server, so no one has access to the server. But you also need to be a bit clever of when you actually return a camera pose, because there might be someone who's trying to figure out what's in the scene by throwing lots of data in it and seeing what's coming out in terms of camera poses. And there might also be a trade-off between like robustness of localization and privacy of the localization process, where if we start making our algorithms more robust, which is what we would typically desire, we might lose privacy as a direct result. Okay, that actually brings me to the conclusion of the talk. I hope I convince you that localization is an interesting and important problem with many interesting applications. Localization algorithms are in general getting more robust and more practically relevant. So we've seen localization services being provided by Google, by Niantic as part of their Pokemon Go and other games. Microsoft through HoloLens is providing those. But also there are many interesting open problems, and especially privacy is becoming, I think, an important issue, where my impression is that people are developing things and they're claiming, oh, this is privacy preserving because it hides this and this information. But my impression is that in many cases, if you take a closer look, it's a bit iffy what they're claiming, and you can actually recover things. And these claims should come with some asterisk on which says under these conditions, which is currently missing. Yeah, that was my thing. If you have any questions, feel free to ask. Yeah.
actually, Martin, you still needs to connect. It lost connection. To back.
But go ahead with the question.
Yes.
I don't understand what kind of damage. I don't understand what kind of damage can occur when some attacker gains access to the data.
I mean, it's depends, right? So if you are sending raw images to a server and someone has access to this, you might have, you say you're playing some AR game in your living room and there's your latest bank statement there, and that's transmitted, right? That's something that might not ruin your life, but it's certainly something that you don't want to share with someone else that you don't know, right? So that would be the motivation for preserving privacy in queries. Privacy in maps is, I mean, it's a question of, I think, communicating of what a user wants, right? So I might not have any issue with someone seeing a reconstruction of my living room or something after I cleaned up documents that I don't want anyone to see, or the basement or whatever. I certainly would not want anyone to see the bedroom of my daughter, because she's young. This is not my place to say I'm happy to share this data. Similarly, if you go to commercial use cases, you might have issues. You could learn about what type of machinery is there, and you could, from that point, draw conclusions about how certain things are manufactured or something like this, right? So it might not always be an issue, but there might also be cases where you really want to make sure that certain information is not somewhere stored on some external server where you have very limited access to, and which might leak this information to someone else. Yeah.
Okay, Adam is the next one.
My view is that as long as you send something to the cloud, I mean, you have the privacy issues, and the only way to prevent that is to not send clouds things to the cloud. So do the localization locally. So is this possible, or are there some factors that make it completely impossible?
I mean, it's possible, but it makes things harder because you need to do all the map building and so on locally as well. So you might need compute, you might need enough so you will need to have the compute. You will need to be able to make these maps available to whatever device you want to use for localization. So it moves a lot of compute responsibility and data sharing responsibility to a user, which might make it harder for certain people to use it, especially if they don't know what the underlying technology is. It can make things harder in scenarios where you have multiple users, or say a company or something, because you will need to update your maps every now and then. You could do this on each device independently, but then you somehow need to fuse that data. And of course you can do this. It might just be easier for a user or for a company as a use case if all this stuff would happen on a server without them having to worry about. So I think there are cases where having a cloud-based solutions makes sense. And I think then the argument for privacy is that yes, you will always leak something, but can you make at least guarantees of what type of accuracy you can get from the server, and what type of information it can leak and what type of information it can't leak. I think there will always be an issue that something gets accessed and you will lose information, or you reveal information to someone that you don't want to reveal it to. But the question is, can we actually design representations that limit this as much as we can, and then can we explore this trade-off between pose accuracy and privacy so that you can actually offer different solutions to parties based on then privacy needs.
Thank you. That was a very precise answer.
Good.
Like, I learned more through this answer, so thank you.
Thank you. Victor will be the next one.
Thanks. So I have a question. Whether you think that this is a kind of a fundamental thing that you need a trade-off between maybe the robustness or accuracy of the system and the privacy, or maybe from your experience it's possible to breach this kind of...
I think there's a fundamental trade-off, because essentially if you're robust to certain variations, you can do what we showed, which is try to take pictures of a lot of objects, send them to a server and see what sticks, where it gets like reasonable poses. And you might still be able to use it if you're clever on what you send back. So you might say, okay, I'm not actually sure whether this image was taken in the actual scene. I might not send back a pose, which for some applications might cause problems because you're only localizing in certain conditions. So when you're not focusing on a single object, but on something like a larger part of the scene, or after a few seconds after you have accumulated enough information that the server is convinced that you're actually still there. I think that then again causes issues in terms of query privacy, because if you need to send more data, that exposes potentially more information to a malicious server. So I think, in general, I think this is very much underexplored. There's a lot of work to do before we actually even start having like meaningful basic answers to standard questions.
Yeah. Thank you for your answer.
Okay, thank you. It was very interesting talk.
Thanks.
So I would have a question. You were showing this approach that was using random lines instead of points. It looks like modulating noise to the actual data and then trying to get rid of the noise after that. Would it be possible? Are there some approaches that would try to scramble the 3D geometry to somehow create kind of different representation of the scene that would still provide you similar localization if you know how to scramble the scene?
Yeah, I think I've seen some, or there's some papers that I know that are on the submission. I think there's going to be like different line generation scheme going to be presented at CVPR. I think it depends really on how you scramble it. I think the way that I see it, that if you have descriptors, you should be able to figure out which kind of descriptors correspond to things that are typically close by. So you can learn about neighborhoods without having to look at the geometry or geometric representation. And then the question is, how much information is still like stored in the scrambled version? And can I recover, based on knowing what should be close to each other, can I recover the global structure of things? That's something that we started looking into. I hope I can give you an answer about around the time of the CVPR submission deadline.
Okay, thank you.
Sure.
Hello, thank you for the presentation. So I have a question regarding the third method of attack you described.
Yeah.
Is it really that big of a problem? Because from what I understood, you can localize, for example, a chair in some scene, and then you want to further build on this representation of the scene. So you, for example, send pictures of a computer, but you actually have no guarantee that the computer will be localized in the same, in the same scene that is actually stored. It might be localized in some completely different, like, apartment. So how do you,
I mean, it depends, right? So what the message that we wanted to show by the paper is that there is another angle of attack, which is you use information that the server is supposed to provide to you, and you can use this to recover something about the scene. Yes, it only works if you know which type, like know that there's a single scene or you attack a certain scene. But yeah, the message more was like, look, there's another piece of information that can be exploited that you should be aware of, especially since this line-based representations, I think, are touted by some companies as privacy preserving. So that should come with asterisks that under certain conditions you get something.
Okay, I see. Thank you.
Just a second, Adam. I have also a question. Imagine you would like to do visual localization inside of this castle. That would be the question. Now the explanation. Imagine that, or not imagine, but take into account that the walls are so thick that you can't rely on connecting to a remote server first. Second, during winter time, the days are short, so it's different lighting conditions inside than in summertime where you have a lot of sun flowing inside, bright sun. There are a lot of mirrors and there are a lot of visitors cluttering around, walking next to you. So how would you approach this problem? Is it already approachable? Do you know of any methods that could try to solve it? I'm not sure. My opinion is perhaps it's not, but maybe you can surprise me by telling me that yes, it's possible. So what about that?
I think it's reasonably possible to get through this. So depends a bit on what you are allowed to use. Are you trying to localize individual images? Then yes, you can always find, like take a picture that you can't localize, take a picture of a white wall. That's never going to work. But if you start having short bursts of images, so you capture things with a smartphone and you're allowed to use the IMU on the smartphone to track the motion in between, then you all of a sudden can localize multiple images at once. You have a larger field of view, which increases the chance that you find some feature matches that are actually meaningful. Visitors typically don't cause a problem there as long as they don't completely dominate the images, because you don't need feature matches over the whole image, but a few regions might be sufficient. And again, also for these strong illumination changes, you might find enough regions where there's not that strong illumination change, so that you can still do feature matching. So yeah, it would come down to an experiment, but I think we could try. I think existing methods might do reasonably well on the console already.
Okay, I am ready to try out. So if you are,
Yes,
we can
sure.
try.
We capture data and we try it. That's not an issue.
Okay, Adam.
So another question. In cryptography, you have something like a private key and a public key. So you encrypt with the private key. No, you encrypt with the public key, and then you need the private key to decrypt.
Yep.
So are you thinking about similar schemes, so that the server does the computation, but only knows the public key, and it sends you back the result, and only the client can decrypt with the private key?
I mean, the scrambling, a 3 model would go, what Jerry proposed would go in this direction, in the sense of that the client, the server would send, say, scrambled geometry back to the client, and then the client could decode this. Might work, might also with using the same argument that you might figure out which parts of the scrambled geometry should be close to each other. You might be able to recover something from the original 3-point positions. And it's a pity that Susanna just left, because she knows more about this. We looked a bit into what is it, homographic encryption, something like this. Homomorphic, yes. The issue there is this is like orders of magnitude slower than what we needed. So we need to do computations in the order of milliseconds, not seconds. And we need to do them, no, actually nanoseconds. And we need to do them thousands of times per query image. And existing methods there are currently significantly too slow. But yeah, we're exploring this a bit, like what happens, what type of information can you use, and when do you start leaking information from this if you try to disguise what you're sending.
Okay, thank you.
So I have one more question. So would it be possible to maybe approach this differently, to train a network to generate features or like descriptors such that, for example, you have like multiple different kind of patterns that project onto the same type of descriptor.
Yeah.
So then it wouldn't be possible to kind of recover, if like a PC, like a corner of the PC and then like a bed or something else, they both have the same descriptor. This makes the problem difficult on like doing the localization, but maybe not so much. But would it be possible to kind of try to learn some sort of ambiguous representation for it to make it able to like just have the scrambled, like kind of hide within the scrambled point clouds this kind of information?
I think that's possible. Where I need to think a bit more about this. So this is something that crossed our minds at some point. The issue is what happens if you actually have not a single image but multiple images. Does this start revealing some information that you don't want to have? So you could actually think of, if you have this ambiguous representation, you get multiple poses that the server would return and would essentially say, you're at one of these positions. Figure out which one it is based on data that only you have. I think that's problematic with motion patterns because so you start with multiple images, multiple potential poses from a single image, and then you start moving, and then that might eliminate a lot of these additional things quite quickly. So there was actually a paper, like what was 10 years ago, that did localization of cars just by looking at when they would turn at which point in time. And even in a relatively large map, after a few turns you could tell where the car is, because this information is like which potential pathways it could have taken was rather unique. So I think temporal information will always be an issue there. That once you start like going from just send a single image to I query frequently, that might also reveal a lot of information.
Thank you.
Yep.
More questions? If not, then let's thank the speaker again.
Thank you very much.